The Janus Point, the book that your most recent book that we're about to be discussing, is about, among other things, the direction of time. And most of us are familiar with the idea of time's arrow in the singular. I mean, namely that it points forward from past to future. But you are careful to refer to time's arrows in the plural and to disambiguate them. And maybe we should start by discussing the three that you take to be most salient. So let me ask first, what is and how do you describe the arrow of equilibration?
Well, that's what really came to the fore in the 1850s, immediately after the discovery of the first two laws of thermodynamics in 1850. And that fairly soon within the next 10, 15 years led to the very precise concept of entropy by Rudolf Clausius. To define it precisely, he had to assume a system that was always in equilibrium and was being moved very carefully, reversibly from one equilibrium state to another. But the very easy way to think about equilibration is if you start off with a sealed box, and in one corner of it there's a small cube of ice, and there's air in the box. Well, bit by bit, first the ice will melt, and then it will evaporate, and the water molecules will be spread out uniformly over the entire box. Now, the original arrangement of the water molecules in the ice is a highly ordered structure. It's a crystal lattice. And then after that, it's all spread out. So this is the paradigmatic example of growth of entropy to maximal entropy, where it's fully equilibrated, and that's, so to speak, that's what one thinks of as heat death. And this made a huge impression. So in 1865, when Clausius actually coined the expression entropy to make it sound like energy, so the two fundamental concepts that he'd identified were energy and entropy, he said very proudly, I can now formulate two laws of the universe. The energy of the universe is constant. The entropy of the universe tends to a maximum. And by and large, I would say the great majority of physicists ever since then have accepted what Clausius said. And I'm very skeptical about it because a key part of making it all seem so clear is that I started off with having that bit of ice, that block of ice in the corner of a big box. And if it weren't for the walls of the box, the molecules would just escape off into space. If that was happening out in space, for example, there's no way you would get that equilibration. And I think a lot of the discussion of entropy has just come about because people haven't thought about how it was originally discovered and formulated.
Mm-hmm. Now, just parenthetically, among many things I love about your book is, the first thing, this isn't what I was going to mention, is that I think the phrase you use is you refer to yourself as a buff of the bard. You're a big fan of Shakespeare. So Shakespeare is constantly making appearances. I actually just finished the book this morning, and I very much appreciated Gerard Manley Hopkins' appearance at the end of the book because he's another figure that I love. But what I was going to mention is you also have a taste for etymology, which I do as well. And you just mentioned Rudolf Clausius's coining of the term entropy. And maybe you could say a bit about the etymology there because it is fascinating.
Now, trophy, it comes from the Greek trophy, which, if I'm not mistaken, it just means transformation. he originally called this quantity the transformation value. And then he just added the En to make it sound like energy. He's quite frank about that. I think that's correct, yes. It's sometime since I'm relying on my memory, but I do find etymology is very revealing. It's very, looking at it, it's very helpful to see how concepts come into existence, and particularly right at the start, very recently, very interestingly, I did know about it, but where the word, what chaos originally meant. Chaos originally it first appears in the very early Greek poet, the contemporary of Homer, Hesiod, where he's talking about the gods. And he says that in the beginning there was chaos, and it really means a gap between something that bounds it, and the word chaos is related to our word yawn. And
really?
yes, that I was aware of. And so it's actually sort of 500 years later before the word chaos in the modern meaning comes in Ovid, the Latin poet's work. And in Hesiod and in the ancient Greeks, it just meant really a gap between some boundary, which is very revealing, I think. And I heard about this in a talk in Oxford a month or so ago, and I commented that the most fundamental, the original dynamical law, Newton's law of gravitating particles, it's all about a gap between particles. So that's the boundary which Hesiod talks about, and the space between, the gap, the void between.
Do you see the relationship between this boundary, this notion of gaps between boundaries, as reflecting in mathematical and physical conceptions of chaos, in which there's this huge disparate boundary between initial conditions and the plethora of later conditions that result from the sensitivity to the initial conditions? There's just this huge gap between the results, or that's not how you see it relating to the etymology?
I think there could be. So I'm not quite sure how, I did put it in the Janus point, but I think it's I'm emphasizing it much more now. So if you're thinking about a physical system, in a laboratory, you can just put a gas in a box and that's it. And so it's either confined, or if it escapes, it's unconfined. However, on the Earth, the gravitational force always keeps us on the Earth. We can't escape from the Earth, well, only with a rocket. But in mathematics, there's a distinction between the key concept in dynamical theory is the phase space. That's each phase is defined by all the positions of the particles and their momenta together. So that's a huge multidimensional space. And the dynamical solutions can explore either a bounded region of it or an unbounded region. And what I'm coming more and more to the conviction is that these two situations are very, very different. And there are this workshop that I attended in Oxford a month or so ago was very interesting. There were 3 talks. One was on chaos, one was on entropy, and one was on complexity. And it became clear to me that all of these, they were very good talks, very interesting, but in all cases, the discussion was about situations where the objects were confined. They couldn't go out all the way to infinity. But the oldest dynamical theory we have is the Newtonian n-body problem. It's the problem of a finite number of gravitating point particles. And the scale in the Newtonian representation, the scale of that system can grow to infinity. And it's just quite different. So I think the two situations are as different as day and night, black and white. And the great bulk of all the work that scientists have done is about systems that are confined, that the technical expression is their solutions only explore a finite region of a region with bounded Liouville measure is the technical term. And it's going to be just quite different. So the question is that an appropriate framework to think about the universe? And I'm getting increasingly of the conviction that that's not the case, that it's quite different.
Well, boundaries will become very important as we get to the recurrence theorem and cosmic inflation. But for now, I just would like to also note that as fun as the etymology of entropy is, one of your collaborators, I think, Flavio Mercati, if I have the name correct, pronunciation correct, also coined a neologism, entaxy, that we'll also get to later, but that is a correlate maybe of entropy. But just to paraphrase before we move on, so the arrow of equilibration is within a closed system, a highly ordered state will move to one of disordered equilibrium. Is that a decent paraphrase? Okay, great. And then there's another arrow which you point has a somewhat funny name, but it's an arrow associated with retarded waves.
Yes.
Could you explain that arrow?
Well, that just comes from the fact that a radio antenna or TV antenna sends out signals, and they go out in principle all the way through the universe. They never come back going in towards the antenna. And that's called the radiative arrow of time. I'm inclined to think that that's just another example of what I was saying about the thermodynamic arrow, because if you were if this was happening in a box, you'd quite soon get a chaotic situation. In fact, actually, now I think about it, the best microwaves are constructed so that the electromagnetic energy is distributed chaotically within the microwave, because then you don't get these hot and cold spots in the microwave. So I think, I suspect that really the radiative arrow is just another example of what one would call the growth of entropy in a confined region. I don't think that's I think I rather skipped over the radiative arrow in the book. I only just mentioned it, but I think at the back of my mind there was already something like that. But now I think about it, the microwave ovens is a very good example of saying, well, it's really the radiative arrow is just the same as the entropic arrow.
Okay, and then the third arrow, and then we can be finished laying out the arrows, is related to wave function collapse. And I don't think that this, well, maybe you will relate it to the thermodynamic arrow, but how do you think of this arrow?
Well, it's a notorious arrow in quantum mechanics, and I guess it's related to the famous problem of Schrödinger's cat, which can be in a state of being alive and dead. So you can imagine that it's in a box, and it's both alive and dead until you open the box and look, and then it's either alive or dead, and that's what is the collapse of the wave function. And it's basically that problem which leads virtually all physicists to say that quantum mechanics is the most fantastically well-confirmed theory. There's a very precise theory of quantum mechanics. All the experiments confirm it. The technical applications are just unbelievable. I mean, we couldn't be talking to each other without very good understanding of engineers of how to do all these things, and it all goes back to quantum mechanics. But yet, at the end, everybody says they don't understand it at all. Now, in the Jonas point, I don't think I made any sort of attempt to grapple with it then, but since then, because of a suggestion I made in the Janus point for what time might actually be, some of my collaborators and I have come to the conclusion that there may not be any wave function at all. We might get around to talking about that later.
Oh, really? So you're the exact opposite of the Everettian.
If that's, well, I was already getting skeptical about the many worlds interpretation before this, but I think we'll leave that for a little bit later in the discussion.